Hey guys, how's it going? All right, guys. So for many of you guys, this could be the last lesson of Math 30-1. Hey guys, congratulations, you made it like that. I hope the course is going well. You're getting the marks that you want for this, and I hope that you're doing well. If you're in my class, we're doing this, and we'll have 3 more lessons after this like that. We do think it's kind of a bit of a weird order at my school, but yeah, for a lot of you guys like that, this is the final chapter in the book. And it's what a lot of courses are finished with. Topic is called the binomial theorem. Okay, so it's this binomial theorem is a topic on how we can it's not a trick like that, but it's a way that we can expand binomials, bigger binomials, very quickly. Has a lot of applications in probability and in number theory and things that you'll cover down the road as well. Okay, so first topic, we're talking about something we call Pascal's triangle. So here's what Pascal's triangle is. It is a triangle made of numbers where the first number over here is 1. And then the second row is 1, 1. We always have 1s on the outside, but the way we can fill in the inside numbers, the interior numbers, is by adding the previous 2 numbers directly above it. So in the third row over here, in the second spot, 1 plus 1 is 2. Again, we have 1s on the outside. 1 plus 2 is 3. 2 plus 1 is 3. 1's on the outside. 1 plus 3 is 4. 3 plus 3 is 6. 3 plus 1 is 4. And we keep seeing these guys over here. Okay, so this pattern over here is going to keep on going indefinitely, and there's a bunch of patterns we see over here. Okay, so first pattern as well. First of all, this guy is symmetrical. Like there's the same thing on the left, same thing on the right over here. I'm just kind of split down the middle over here. We have 1s on the outside. Okay, if you look at over here, we have the natural numbers in kind of this diagonal column over here as well. These numbers over here are what we call the triangular numbers. They're called triangular numbers because if you draw a triangle, we'll start with 1. There's 1 dot. And then if I draw a triangle like this, that's 3 dots. And then if I keep adding, that would be 6 dots right there. If I draw another one like this, that is 10 dots and so forth like that, because there's what we call triangular numbers there. Okay, so guys, there's a bunch of patterns over here that we do. I haven't really proved why these numbers work the way they do, okay, like that, but it's not really too important for what we're doing over here. But this triangle, guys, it's full of a ton of, I think they're interesting patterns that you can see as well. So here's the pattern that we're going to be looking at this one. If you look at this row over here, okay, we tend to call this one the n equals 5 row. Okay, and that's coming from like the 1, 2, 3, 4, 5. So there's the n equals 1 row, the n equals 2 row, the 3 row, the 4 row, the n equals 5 row. Now what you see though here, this is actually the n equals 0 row. So we're actually starting at n equals 0. So the n equals 5 row is actually the 6th row in the triangle. Okay, but for the n equals 5 row, where's the number 1 come from? Well, this is really the same thing as 5 choose 0. Where's 5 come from? Well, 5 is the same thing as 5 choose 1. 10 is 5 choose 2. 5 choose 3. 5 choose 4. And then 5 choose 5 over here. Okay, so what the next bullet says, using the pattern with combinations, list the 7th row of Pascal's triangle. Okay, well, the 7th row is the same thing as what we call the n equals 6 row. And remember, it's because, well, the second row is the n equals 1, the third row is the n equals 2, the fourth row is the n equals 3, the fifth row is the n equals 4, so that means the 7th row is the n equals 6 row. Well, what's this going to be? is going to be 6 choose 0, 6 choose 1, 6 choose 2, 6 choose 3, 6 choose 4, 6 choose 5, and 6 choose 6. This is 1, this is 1, this is 6, this is 6, this is 15, this is 15, and 6 choose 3 is 20. Okay, so this is kind of how Pascal's triangle is kind of working out for this guy right here. We see 1, 6, 15, 20, 15, 6, 1. This is the n equals 6 row. Okay, another pattern over here. If this is the n equals 6 row, there's actually 1, 2, 3, 4, 5, 6, 7 terms. Okay, so there's 7 terms in the 7th row. But if we call this the n equals 6 row, and we'll explain that more in the next example, there's actually going to be 7 terms in that guy. Okay, example 37. So the topic is called the binomial theorem, and in each of these, a plus b to the 0, a plus b to the 1, a plus b squared. Well, the part inside a plus b is a binomial. There's 2 terms over here and here. Okay, well, a plus b to the 0 is just going to equal 1. Okay, a plus b to the 1 is just going to be a plus b. Now, what I'm going to do over here, though, I'm just going to write this guy as 1a plus 1b, and you'll see why I'm going to be doing this in a second here. A plus b squared. Okay, so when we do a plus b squared, this means the same thing as a plus b times a plus b. A times a is a squared, and I'm going to write this as 1a squared plus ab, this and this. B times a is ab again, plus b squared. So we got 1a squared plus 2ab plus 1b squared. All right, well, a plus b cubed is the same thing as a plus b times a plus b squared. Well, we already know what this answer is here. We figured out in the last example to be a squared plus 2ab plus b squared. Okay. Now, if I can expand this out again, the a gets multiplied to every term over here. So we get a cubed plus 2a squared b plus ab squared. Now the b gets multiplied through the brackets, plus a squared b plus 2ab squared plus b cubed. Now what this is going to end up being is 1a cubed. We have 2a squared b plus a squared b is 3a squared b. ab squared plus 2ab squared is 3ab squared plus 1b cubed. Okay, one more. A plus b to the 4th is the same thing as a plus b squared times a plus b squared. Okay, I'm just going to do this over here, which is the same thing as a squared plus 2ab plus b squared, a squared plus 2ab plus b squared equals a to the 4th plus 2a cubed b plus 2a squared b squared plus 2a cubed b plus 4a squared b squared plus 2a b cubed plus a squared b squared plus 2ab cubed plus b to the 4th equals 1a to the 4th. We have 2a cubed b plus 2a cubed b is 4a cubed b. 2a squared b squared plus 4a squared b squared is 6a squared b squared. We have 2ab cubed plus 2ab cubed is 4ab AB cubed plus 1b to the fourth. Okay, so I want to kind of just, I know there's a lot of work over here, guys, but one of the points we're trying to make here is when we need to expand out binomials like this, it can take a long time like that. It's pretty painful to have to do this. Like, and this was only a plus b to the fourth. Imagine doing like a plus b to the 10th, or a plus b to the 12th, or a plus b to the 30th. Okay, that would spend a ridiculous amount of time. And really, guys, ain't nobody got time to be able to go and do something like that, right? So what we're going to do here is I'm just going to rewrite these guys over here. So we had a plus b to the 0, a plus b to the 1, a plus b squared, a plus b to the fourth, cubed, and then the last one was a plus b to the fourth. This answer over here was 1. This answer was 1a plus 1b. This answer, 2a squared, 1a squared plus 2ab plus 1b squared. The next guy was this guy, and our last one was because what I'm trying to get, hopefully that you're seeing here, is that these coefficients follow the exact same pattern that we saw on Pascal's triangle in the first example. Okay, so what was happening here is the coefficients on each of these terms are following the same exact coefficients that we see in Pascal's triangle. The other pattern that we see, so if we look at this one, for example, every term in order here. So first of all, it's 1, 4, 6, 4, 1 is the same thing as 1, 4, 6, 4, 1. We started with an a to the fourth here, and then we went a cubed, a squared, a to the 1. Okay, we started b to the fourth at this term, b to the fourth, and it was b cubed here, b squared here, and b to the 1 here. This is really actually b to the 0, which is just 1 over here as well, and this is really a to the 0 over here as well too. Okay, but we just typically don't write those guys over here. So the pattern in Pascal's triangle that we see here is going to be able to help us expand binomials to larger exponents. So when I said that this guy over here was the 1, 2, 3, 4, that pattern over here, this was the n equals 1 row. Well, the 1 is this exponent over here. If this was the n equals 2 row, well, that was the exponent here, a plus b squared. This guy was the n equals 4 row, and that's corresponding to the a plus b to the fourth on this guy over here. So what the binomial theorem is saying is that we can expand any power of a binomial expression of x plus y to the n, where n choose 0, n choose 1, n choose 2, and so forth like this. Well, this is really the n row on Pascal's triangle. N choose 0, n choose 1, n choose 2, all the way up to n choose n. Okay, so, or we can just look at Pascal's triangle and be able to do that. So example 38 is saying, using binomial theorem, Pascal's triangle to expand each binomial. Okay, well, Pascal's triangle is so here's our row 1, 6, 15, 20, 15, 6, 1. Okay, so we're doing x plus y to the sixth. Okay, this 1 is really 6 choose 0, 6 choose 2, 6 choose 3, 6 choose 4, 6 choose 5, and then 6 choose 6. Guys, I forgot all about 6 choose 1 here, but 6 choose 0, 6 choose 1, all the way up to 6 choose 6. Okay, so what I'm going to just do over here, and that was like what this part is saying over here. Guys, we don't need to have this one memorized like that. We actually have a formula on our formula sheet that we really use. We could just use Pascal's triangle. I'm going to write down 1, 6, 15, 20, 15, 6, 1. Okay, so the pattern starts, if this is x plus y to the 6, I start at x to the 6, x to the 5, x to the 4th, and I just keep going down. And this guy over here will be an x to the 0, but I don't need to write that. Now, my last term is going to be a y to the 6th here, and I'm going to start counting backwards like this. And then we put pluses in between them because we're adding up all these terms. So our final answer would be x to the 6th and this is our binomial expansion for x plus y to the 6th. Okay, again, this way over here, once you learn this technique, like if you have to expand something like this, this is going to be a much better way to do this question. 2x minus y to the 4th. Okay, so we're going to start, and guys, you don't need to write this out every time, but I'm going to for this example. We're going to start with the n equals 4 row. So this is the n equals 1, 2, 3. This is the n equals 4 row over here. So we have 1, 4, 6, 4, 1. Okay. What's a bit different over here is that our first term is actually a 2x. So this is going to start as 2x to the 4th, 2x cubed, 2x squared, and then 2x. Our last term is going to be negative y to the 4th, negative y cubed, negative y squared, negative y to the 1. We're going to put pluses in between here, and I guess this is going to be temporarily pluses in between them, and you'll see why in a second. So the first term, we get 1 times 2x to the 4th. Well, 2x to the 4th is the same thing as 16x to the 4th. Okay. Now for this term over here, we're doing 4. 2x cubed is the same thing as 8x cubed times negative y. Ends up being 4 times 8 is 32, but it's going to be negative 32 x cubed y. This guy here is going to be 6 times 2x squared is 4x squared times y squared. 6 times 4 is 24 x squared y squared. Our last one here, we have 4 times 2x times negative y cubed. 4 times 2 is 8 times negative is negative 8x y cubed. Our last one, negative y to the 4th, is just going to be positive y to the 4th, written like this. So here's our answer for 2x minus y to the 4th. Okay. 3x squared plus 4y cubed cubed. So in this case, our n value is 3. So we're using this row. Our n equals 3 row for Pascal's triangle. And we're at 1, 3, 3, 1. We have 3x squared cubed. We have 4y cubed cubed, 4y cubed squared, 4y cubed to the 1, plus is in between. 3x squared cubed is 27, x to the 6th. 3 cubed is 27, x squared cubed is x to the 6th. Okay. Over here, we're going to get 3 times 3x squared squared is 9x to the 4th times 4y cubed. 3 times 9 is 27 times 4 is 108 x to the 4th y cubed. Here we get 3 times 3x squared. 4y cubed squared is 16y to the 6th. 3 times 3 is 9. 9 times 16 is 144. So we get plus 144 x squared y to the 6th. 4y cubed cubed. 4 cubed is 64. Y to the 9th. And here's our answer for this. All right, x minus 1 over x squared to the 4th. Now, the way I'm going to recommend that you do this question, it works out easier with the exponents. If we write this, 1 over x squared is the same thing as x to the negative 2, okay? So this is going to work out better with the exponents for this question. So again, Pascal's triangle. So we're using the n equals 4 row right over here. So we have 1, 4, 6, 4, 1. Our first term is x, so we go x to the 4th, x cubed, x squared, and x to the 1. We come back the other way. We have x to the negative 2 to the 4th. Sorry, that's negative x to the negative 2 to the 4th. We have negative x to the negative 2 cubed. Pluses in between. Here, we get negative x to the negative 2 is 1. So negative 1 times 4, so it's going to be a minus 4. We have x cubed times x to the negative 2 is x to the 1. Plus negative x to the negative 2 is positive x to the negative 4. So plus 6x to the negative 2. Okay, x to the negative 4 times x to the 2. 2 minus 4 is negative 2. Those are exponent rules here. Here we have, I'm going to write this one out here. We have 4x times negative x to the negative 6. So this is going to be negative 4 x times x to the negative 6 is x to the negative 5th. And our last one, negative x to the negative 4 is going to be a positive because we're taking a negative to a positive to an even exponent, x to the negative 8. So this gets x to the 4th minus 4x plus 6 over x squared minus 4 over x to the 5th plus 1 over x to the 8th. And this is x minus 1 over x squared to the power of 4. Okay, so for example 39, using the general term of a binomial expansion formula off your formula sheet, and I just put this guy right here for you guys. So this is on your Math 30 formula sheet. Refer to that one. In the expansion of x plus y to the n written in descending powers of x. That's kind of the way we did it. We started x to the high power and we counted down. The general term is this exponent over here. Okay, so what they're asking us to do here is figure out the fourth term of this guy over here. So that means we have t4. Okay, well, the formula we have is t to the k plus 1 equals n choose k, x to the n minus k, y to the k. Okay, so what do we have so far? If this is t4, k must be 3. Because t4, it's 3 plus 1 to give us t4. Okay, now our n value is this value over here, n equals 6. Our first term is 3x squared. Our second term is negative 2y. Okay, so we have t3 plus 1 equals 6, choose 3. Our k value is 3. Our x, which is our first term, is 3x squared to the 6 minus 3. Our second term, negative 2y cubed. Okay, 6 choose 3 is 20. Okay, this 6 minus 3 is just 3 times 3 cubed is 27, x to the 6, times negative 2 cubed is negative 8, y cubed. Guys, I'm just going to do this on my phone because I don't have my calculator right in front of me right now. We have 20 times 27 times negative 8 gives us negative 4,320 x to the 6 y cubed. Okay, so what this is telling us over here is, I'm going to show you another way of kind of why this formula works. This was the n equals 6 row of Pascal's triangle here. If we're going for the fourth term, that was this guy over here. Okay, now if you remember, this number was 6 choose 0, 6 choose 1, 6 choose 2, 6 choose 3. This would be 6 choose 4, 6 choose 5, and 6 choose 6. Okay, now, well, hopefully we'll just see the pattern over here. If we want the fourth term, you see how this 3 is actually one less than the term number over here? This is the third term. This is 6 choose 2. The second term is 6 choose 1. The seventh term is 6 choose 6, and so forth. Okay, so the term number is always one less than this value. So that's why the formula is tk plus 1. Okay, this number here, n choose k, gives the 20, which is the coefficient right here. Okay, now our pattern works where this would have been 3x squared to the 6, 3x squared to the 5th, 3x squared to the 4th, and then 3x squared cubed. Okay, that was this part here, 3x squared cubed. Then going this way, it would have been negative 2y to the 6th, negative 2y to the 5th, negative 2y to the 4th, and this guy would have been negative 2y cubed, which was negative 2y cubed in this formula over here. Okay, so this is kind of how this formula works, and guys, you'll see questions just like this. We're going to give you an expansion like this, and they're going to ask you for the fourth term. We're just applying this formula over here. Second term. Okay, so in this one, we want t2, and our formula was t to the k plus 1 equals n choose k, x to the n minus k, y to the k. So for t2, okay, this means that k equals 1. because tk plus 1, so for t2 this value must be a 1, equals our n value is 7. 7 choose 1, x to the 7 minus 1. Now, same thing over here, guys, like in the last one. I'm going to go negative y to the negative 2 instead of 1 over y squared here. It works easier with the exponents, I think, when you do it this way. And our k value is 1, so it's going to go right here. 7 choose 1 is 7, x to the 6 times negative y to the negative 2 is negative 7x to the 6th over y squared. This will be this guy here. Okay, guys, last example. In the expansion of 3x minus 2y cubed to the 5th, one of the terms is ax cubed y to the 6th. Determine the value of a. Okay, so here's what we're going to do here. Now, the problem is, here, we don't know if this is the first term, second term, third term, fourth term, fifth term, sixth term, or any of those. But, so we don't know, that means we don't know k. Okay, now we're going to go tk plus 1 equals n choose k, x to the n minus k, y to the k. Now, for the moment, I'm just going to leave k as a variable in this equation. We'll switch it out once we figure it out in a sec. Now, our n value is 5. Choose k. We have 3x to the 5 minus k, negative 2y cubed to the k. Now, hopefully, guys, what we're seeing here is this answer was a y to the 6th. That means this term here must end up being something y to the 6th. Now, if this is y cubed, I'm taking to the power of k, therefore, k must equal 2. Okay, so once we solve for, figure out what k is, and we just look over here, and if we look at this term as well, if I go 5 minus 2, I get 3, and I got 3x to the power of 3 is going to give me this guy, x cubed. So if I figure out my k value is 2, I'm going to come back, t to the 2 plus 1, so I'm looking for term 3, is 5 choose 2, 3x, 5 minus k is 3, negative 2y cubed squared. 5 choose 2 is 10, 3x cubed is 27, x cubed times 4y to the 6th equals 10 times 27 times 4 is 1080 x cubed y to the 6th. Okay. Now this question was saying a x cubed y to the 6th, and we had to figure out what a was. So hopefully you see that a is the same thing as 1080. All right, guys, so this is how the binomial expansion works, guys. Make sure you're keeping up with your practice, and please come and let me know if you have any further questions, guys, and I'll see you in the next video. Bye-bye.